think this is it. Okay. You got it? Hear me? Okay, how's that? So I want to talk to you today about this sequence, OBAFGKM, aka the Harvard scale, and how it came to measure the brightness of stars. I actually got there here. So it's a scale where the brightest stars are obviously O, and that's the letter O, not 0. And then it's B, and then of course it's A, duh. And then clearly the dimmest ones are going to be M. And so, yeah, that's all very intuitive. And I mean, I guess that's it. I suppose I'm supposed to give some kind of toast now or something? No, wait, that's not intuitive. It's not intuitive at all. It's not intuitive at all. So unintuitive that the astronomers had to make up ways in order to remember it. It started in the 1920s, and the original mnemonic is, "Oh, be a fine girl, kiss me." Since then, there have been many more, including this response. Only boys accepting feminism get kissed meaningfully. And also, oh boy, astronomy final is going to kill me. But why was it that place in the first place? And why not just alphabetical order? To answer that fully, we need to start from the very beginning, which is a very good place to start. We've always had a vast array of stars in the sky, tiny lights with different brightnesses and different colors, varied arrangements. Where did I put this? There we go. That's where I put it. In the Western civilization, the Greek astronomer Ptolemy, on the left, looked at the stars he could see and grouped them into 6 magnitudes of brightness, where 1 was the brightest and 6 was the dimmest. Galileo took a telescope and pointed it to the sky and found a whole lot more stars Ptolemy could not see, and he was able to see down to 9 magnitudes. Now, this is all well and good, but Ptolemy and Galileo had one big problem. They had based their observations on what they could see from Earth, and their observations could lead to the conclusion that the sun was the biggest star ever, and all the others were just teeny tiny stars. And I think this problem is best explained by the noted astronomer, Father Ted. Is this going to go?
These are small, but the ones out there are far away. Small, far away.
Thank you and welcome to my Father Ted Talk. They measured what was termed apparent brightness, which is how bright something looks from Earth, and not absolute brightness, which is intrinsic. Here's the Big Dipper to show that stars we think are right next together are not actually right next together. We can see the distance on them. The one that's the farthest away is many more times brighter than the other ones. At Galileo's time, there was no way to calculate distance to the stars, so a method needed to be made that calculated brightness without needing to know distance. In the 1850s, a small step was taken toward this by Jesuit astronomer Angelo Secchi. It was known that if objects glowed, you could determine their makeup by passing that light through a prism and observing the spectrum of colors. So Secchi put a prism in his telescope and observed the spectrum of light he saw coming from the stars. Each of them have different vertical dark lines going through the spectrum of colors that indicates presence of different elements. And he split all the stars into 4 groups. However, like every astronomer before him, he could only describe what he saw. There was no way to preserve or share the actual images. In 1873 came Henry Draper, here with the telescope built into his house. How do you get a telescope built into your house? You marry the heiress of a railroad company. He was he was a doctor and amateur astronomer who was also a big photography fan. So he took some of the very first photographs through a telescope. He and his wife Anna took hundreds of photographic plates with many stars each, like that one. And they also took pictures of the star spectra so that they could see what the stars are made of. So this is black and white. That's what they had, and you actually needed a magnifying glass to see the actual spectra. So this is what we got. Unfortunately, Henry Draper died of illness at 45, and Anna continued the work on her own, but found it difficult to get help. In 1883, Edward Pickering, who ran the observatory at Harvard and had admired Draper's work, wrote to Anna offering to help. Anna, who desperately wanted to see the work continue, gave the hundreds of plates and the telescope to Harvard and endowed a fund to carry on the work. She also visited frequently to check the progress. So, Edward had all these plates with all these hundreds of stars and telescopes to photograph more. So what did he do? He hired women. He hired a lot of women. Over his time as director, he hired 80 women to classify stars. They were called the Harvard computers, as computer was the actual job title at the time. He paid them half as much as a man would make. But there were opportunities where few such existed. The work was detailed and painstaking. They had to record and classify every single dot on a plate. At this point, I wanted to state that the work done by Pickering and the Harvard computers provided the foundation of modern astronomy as we know it today. I want to list some of the discoveries made by these women either during or after their time. Cataloging over 300,000 stars, nebulae, and comets. Determining the temperature, brightness, distance, and composition of stars, and the discovery of new kinds of stars. There could be several talks here, but I'm only doing one. There's an unsupported story that Pickering first hired men and were so frustrated by their work that he exclaimed, "My housemaid could do better," and fired them. However, it's an actual fact that the first woman he hired was in fact his housemaid. Recommended by his wife as a woman with skills beyond the management of a house. Wilhelmina Fleming. She was a Scottish immigrant with no previous scientific experience. She started work in 1881 at the age of 24 and did her own work as well as managing the other women. Okay, here's where it gets sciencey. She took the collection of star spectra and sorted them by how big their hydrogen lines were, meaning the most hydrogen detected to the least hydrogen detected, and labeled them alphabetically from A to O. Okay. So you on the top row, you can see there's a black line around the blue and a black line around the green up on the very top. And those are hydrogen lines. When they're fat, that's lots of hydrogen. As they go down, that's less hydrogen. So if you saw a star and it looked like the top one, that'd be an A star. Then further down, that'd be a B star. In 1896, Annie Jump Cannon was hired. She was 33 years old and was deaf due to scarlet fever as an adult. She was incredibly fast at classifying stars by their spectra and could do 200 stars an hour. She did hundreds of thousands of stars in her career. Edward Pickering said publicly there was no man or woman faster. She would take a plate like this, and we're going to zoom in on it. Each smudge is a spectrum in black and white. She had to examine each smudge with a magnifying glass and match it to the patterns that we just saw. She could do 3 a minute. Having seen so many stars, she saw her own pattern in them. She took Fleming's system and resorted and reduced the categories to the now familiar OBAFGKM sequence, keeping the letters because the stars had already been classified as such for several years. So you can see on the top right, the O is now on the top. Used to be on the bottom, it's now on the top. And looks more like the B spectrum just below it than the M spectrum at the bottom. There's less lines running along the top and more lines running along the bottom. Also, when you see O stars, they're blue-white, just like B and A stars, and not red like K and M stars. This aesthetic observational method is how she built her system. She didn't have any other data to base it on. It wasn't there yet. Other astronomers found it useful as a way to organize by color and similarity and thought it might approximate brightness, but it wasn't until a few years later when another Harvard computer, Cecilia Payne, was able to show definitively that Cannon had come up with a temperature scale of stars from hottest to coolest and also brightest to dimmest from 96% of the stars. This is a scale that was both aesthetic and meaningful. You can see the O stars are at 40,000 Kelvin and 100,000 times brighter than the sun. And next, the B stars are 20,000 Kelvin and 1,000 times brighter than the sun. And now you're going to say, hold up, Chris. Why is it that the O's were at the bottom, the very bottom of the scale, and now they're the biggest and the brightest? It's because those hydrogen lines that they were using only measure the amount of hydrogen atoms. And when you're at temperatures of 40,000 K, hydrogen atoms lose their electrons. They just fly off, and you get ions. And ions don't show up in those lines. So that's why the O's look like the lowest, but they're actually the hottest and the brightest, and why the only somewhat less hot B stars are next. And it's the A stars, which kept their atoms, that look the hottest to start with. In 1922, Cannon's scale was adopted by the International Astronomical Unit as their official star classification method. And with some additions for special cases, continues to be the star classification method that we use today. Yeah, all the other ones, they're just so. So for real this time, let's raise a toast to weird ordering systems and for people who do the hard, unglamorous work needed to make them happen.